All right, Mike, we are live. So, good afternoon, everybody. Thank you for joining us today. A couple housekeeping items up front, but I am going to drag it out for a minute or so while we have people entering the weight room still. So, my name is Sarah Patry. I am the executive director for PCI Northeast. We are a chapter of the Precast Pre-Stress Concrete Institute. Today, we're hosting this webinar on our solid deck beam guidelines that were published earlier this year. Just a couple of these housekeeping items. If you do have questions, please use the Q&A feature, not the chat feature. I'll still go through the chat and be checking, but it is a lot easier for us to see it in the Q&A feature, and we will do those questions at the end. This does say that the presentation is recording, just to let you guys know that is going on in the background. And this course has been credited for 1 PDH. Mike, I can't see your slides anymore if you want to reshare your slides.
I got kicked out of the meeting for a second, so I came back in. I apologize.
Oh.
Hopefully that won't happen again. But
all right.
you should be able to see the screen now, right?
Nope,
no.
I still can't see the screen.
I'm working on it. I'm sorry.
That's all right.
Well, welcome to technology.
They can hear you, but all right, now we can see it. Perfect.
Yep.
So this presentation has been accredited for 1 PDH. It is not AIA accredited, but we do have the PDH. The credits will be distributed through the rcep.net program. If you have not used this program before, the way that it works is we will submit your attendance as long as you have attended for the majority of the session. We will email those over to RCEP, and within 2 weeks, you will receive an email from them directly linking you to your account. You will have to check your spam folder. If you don't see something by Labor Day, please reach out to me and let me know. Once you log into your account there, you will see this PDH along with any other PDHs that you've taken previously from PCI or anything that you take in the future. If you are watching this in a group setting in your office and only one person is logged in, if other people around the table need a PDH for this, please feel free to email me first name, last name, and email so we can get that submitted along with everybody else's attendance. So if you are doing that group setting, please send me an email later today. So with that, I am excited to introduce Mike Como. He is the Chief Engineer for CHA Consulting. Mike has been a structural engineer for 40 years in the bridge and highway design sector. He has extensive experience in the design of steel, concrete, and pre-stressed precast concrete bridges. He's been responsible for managing design teams on brand new expressway bridges, highway interchanges, bridge rehabs, and other highway structures. He has a special expertise in the field of accelerated bridge construction technologies, and we're really excited to have him on board today. So with that, I'm going to send it over to you, Mike.
Thanks, Sarah. I'm going to apologize ahead of time. My signal's a little glitchy. It kicked me out a few minutes ago. Hopefully that won't happen again. So anyway, it's a pleasure to be here to talk today about solid deck beams and the presentation given for the PCI Northeast Bridge Technical Committee. Those of you who don't know about the committee, it's a committee that was formed around 1990. I've been a member since 1990, so gosh, 34 years I've been on this committee, and this committee has generated many, many documents and guidelines for precast and pre-stressed concrete bridges. So today, for example, if you're familiar with next beams, this committee developed the next beams. And as we always keep moving forward with new ideas, and the latest idea we came up with is this concept of solid deck beams we're going to talk about today, which is a new exciting option for short span bridges. A lot of short span bridges built with voided slabs and precast slabs need replacement. And this is a great, a more robust version of that type of bridge that was developed by the committee over the last few years. This was published and is on the PCI Northeast website. You can download guidelines, which I'll be going through today in detail. www.PCINE.org. You can download everything I'm showing today. So learning objectives for today is become familiar with this new bridge product. It's a pretty exciting thing for us. Learn about why we developed them and what are the limitations of the beam. But then also we'll get into how to design in detail these solid deck beams A lot of engineers want to have answers to those types of questions. How do I design it? How do I detail it? And then really we're going to spend some time talking about how to connect the beams together, which is a key feature in these beams when compared to older adjacent slab bridges that were built years ago. So one of the reasons we developed this beam is we looked at span ranges of current pre-stressed beams that are available in our market in the Northeast. And start from the bottom up. Bulb tees have been used for quite a while. Spans anywhere from say 50, 60 feet up to even over 150 feet. Next beams were developed a few years ago. As you can see, next beams typically we see them used in the 40 to 70 foot range. Adjacent box beams, we've seen them used in the 40 to sometimes up to 110 foot span range. But anything less than 40, we previously would use adjacent slabs. And the problem with adjacent slabs is where we've had issues. I'll go into issues we've had with joints between adjacent slabs, but we're really trying to focus on that short span market, the 30 to 50 foot range for a lot of your smaller bridges that are out there. And the problem with adjacent slabs built to date is the joints. The joints tend to leak. There's a whole bunch of reasons why. I'll go into some of them today. But it's just a fact that these things have not performed as well as we would have liked. We've added toppings, but we've had issues with toppings as well, and I'll get into that as well. So here's just some photos of typical adjacent slab bridges that are in the market today. These are details from bridge manuals. I believe the one is the Connecticut Bridge Manual, the one is from the Massachusetts Bridge Manual. What are the advantages of these slab bridges? They're very thin. If you want a thin superstructure to get over a short river crossing or an overpass, they're great because they're very thin structures. They're also fast construction. They go together quickly. But historically, we've had issues with the joints, leaking through the joints. And I also put in there difficult to fabricate. Fabricating with voids is a challenge in the shop. It can be done, but it's just it tends to complicate the fabrication. But back to, again, the leaking through the joints have historically been a problem with these bridges. So one question is, why do the joints fail? And I've read probably 20 research papers on why the joints fail on these bridges. And there's actually a new one out now by University of Cincinnati, published a recent paper that may result in a change to the AASHTO LRFD specifications. I'll cover that in a minute. But most of the papers I've read have honed in on the fact that we design these bridges essentially as a one-way slab. We have literally hundreds of strands running from abutment to abutment, but laterally we typically just put a few strands transversely to tie these beams together. Well, the reality is these bridges behave as a two-way slab. If you think about live load in the center of a bridge, the interior beams will deflect more than the exterior beams, especially with a concrete barrier, which stiffens the exterior beam. So you get this kind of dishing effect in the structure. So what happens is we end up with these transverse bending moments along the joints. So the joints near the parapet see negative bending, and the joints in the center experience positive bending. And we see this in the field. Historically, the first interior joint from the barrier is the one that leaks first. It kind of backs up this theory, and this has been proven with finite element studies done by researchers. So we're putting a lot of strands in the longitudinal direction, a handful of strands in the transverse direction, and every research project I've read to date says that you need a lot more transverse post-tensioning to get these to function properly, a lot more, like 10 times more than we use now, which is really unrealistic. The last bullet is the research being done at University of Cincinnati, where they looked at thermal gradients may play a role in at least the initial cracking of these joints, with the top of the beams expanding and contracting more than the lower portions of the beam, leading to tension across this joint, leading to cracking. So there are several reasons why we have failure in these joints. So previous solutions, including adding a topping slab, a lot of states in our region now add topping slabs. We also looked into increasing transverse post-tensioning. We found for high volume roads, this didn't seem to solve the problem. Then we started adding topping slabs. The problem with topping slabs is it adds thickness to the structure, so you're losing some of that benefit of structure thickness. You're adding cost. Reinforcing in concrete costs money. We're adding that to the project. And even with these measures, we're still starting to see reflexive cracking over the joints, even with the topping slabs in place. So for all these reasons, our PCI Northeast Bridge Tech Committee decided to come up with a better solution. And I'll give credit where credit is due. Vermont Agency of Transportation, VTrans, was the first state to experiment with this. Connecticut DOT also did it about the same time. This idea of let's try to come up with a better connection between adjacent slabs. So we want to take advantage of the recent deck level connection research that was done as part of the ABC initiative in the US. If you look at our next D details, we are connecting the top flange of the next D with a reinforced closure joint, either with UHPC or regular concrete. The idea here is to marry those details with a voided slab or a solid slab and have a reinforced concrete joint between the beams, as you can see in the cross section on the bottom right. We also look to eliminate the topping slab. That's one of the reasons here. The drawing shows an optional overlay. They can be done without an overlay. That's possible. If state desires to have a bare concrete deck, that can be done as well. But we also, you notice we've eliminated the voids. And really, that was just to reduce fabrication costs. We're trying to be more economical with these sections. And the reality is the voids don't take away that much weight of the section and simplify fabrication, actually end up with a more robust section as well. The key thing is what we're trying to do is emulate a cast in place solid slab bridge. And the term emulation is a term that we use for where we emulate a cast in place structure using precast elements that are joined together. At the end of the day, this bridge essentially behaves as a solid slab from corner to corner. Now, what's nice about that is the AASHTO LRFD bridge design specifications have provisions for solid slab bridges, for live load distribution and for design. So we can take advantage of a lot of the AASHTO provisions when we design these bridges, which really simplifies the design aspect of putting a set of plans together. So we put together these recommended guide details. They were published this year in January, so they're hot off the presses. And the diagram in the upper right shows the cover sheet of what these look like. And what they are is they're 11 by 17 sheets with a whole bunch of information and a whole bunch of details, which we'll go over now. Before we get into the details, look at some photos of actual bridges being built. This is the photo on these photos are all from Vermont. Bridges that were built in Vermont. As you can see, you can do some interesting geometries. This bridge actually had the abutment had a kink in it. You can do sidewalks. Really, anything you could do with an adjacent slab bridge that you did before, you can do with these beams. Really, what we're changing is just the connection between the beams. So the details on the left show the fabrication. This is from Carrera Fabricators, and just showing the bars. The concept here is to have bars projecting from the side of the beam. They overlap in the closure joint, and you fill the closure joint with either concrete or UHPC to make the connection of these beams. A much more robust connection when compared to the typical handful of strands that we've been using in the past for voided slabs and box beams. So some of the key features, again, no voids, a relatively deep shear key. It's almost a full depth shear key. And there are significant bars projecting from the sides. We recommend 6 inches on center for the bars coming out. We're also saying straight strands only. Well, in theory, you could do some draping, and we've seen some designs with draping. Really, draping adds complexity to the fabrication that really isn't necessary for a short span bridge. So we recommend straight strands only. We do allow debonding as states allow. The nice thing about this is that differing from the next beam, where the fabricators had to go out and buy expensive formwork to build next beams, this beam can be built by any fabricator in the Northeast using their standard beam beds that they currently own. The only difference is they need to make new side forms, which is a minor cost to the fabricator. So what's great about this is we can implement this beam without significant investment in formwork, which inevitably gets passed on to the owner. In this case, there's almost no cost additional to make these beams today. It's not something where fabricators have to make huge investments, which is a nice added benefit. As far as the connection details, we're taking advantage of the technologies we learned over the last 10 years with ABC. And these details essentially are very similar to the details we use for next D beams. The question is, how do we size the bars that come out of the side of the beam? How do we design this connection? What forces are going through the connection? Well, if you go back to what I said before, we are emulating a cast in place concrete slab. Well, the AASHTO provisions do have provisions for distribution steel, which is bars that are perpendicular to the main reinforcing steel in the slab. Well, we can calculate the area of distribution bars, which now become the connection bars. So essentially, we're emulating a cast-in-place slab that would have distribution bars running from side to side. We're just lapping the bars in each closure joint. So the provisions for AASHTO are used to calculate the size of the bars that we need for these connections. We've done a bunch of preliminary calculations on preliminary designs, and number 5s and 6 work in almost every case. So that's what we'd recommend you start with. And in most cases, you should be able to get away with number 5s and 6. The key thing is we want to maintain 6-inch spacing because the fabricators have built side forms, and we'll show pictures of the side forms later on why we want to maintain that 6-inch cadence. As far as the joint material, we recommend either using 4,000 PSI or 4 KSI concrete, but you can also use UHPC if you desire. And the details shown to the right are the details that are included in the guide details. I'll cover these in more detail in a little bit. So let's dive into the sheets. Once you get past the cover sheet, we have several sheets with frequently asked questions, and I'll just quickly go through some of these questions. You can read them at your leisure. Well, the first section is general questions. We get asked a lot, is this a proprietary beam section? As you heard a few minutes ago, every fabricator in the Northeast can make these beams, so they're not proprietary by any means. And I won't go through all these questions, but you can take a look at those. Question about utilities, and our recommendation is use the same details you would use for an adjacent slab bridge previously. Either hang the utility off the side of the bridge, or if you have a sidewalk, you can sometimes accommodate a utility under the sidewalk and spread the two beams in that area. We have questions on bridge geometry. We always get asked questions about span length and skews, and I'll cover span length in a little bit, but basically we can go up to about 56 feet with span length. Skews, we recommend a maximum skew of 45 degrees, but we'll get into beam widths and the widths that are available. Previously, with adjacent box beams and adjacent slab bridges, we've had two widths, roughly 3 feet and roughly 4 feet wide. Our fabricators in the committee said, well, we can make it almost any width you want. So now we have 4 beam widths, and that's item 7. We go from 35.5 inches to 47.5 inches in 4-inch increments. We'll talk about that a little more later as well. Next page, sheet 2 of the frequently asked questions. We have design questions talking about how you design these bridges. And again, I'll cover a lot of this in the subsequent slides, but we have recommendations in the guide details on how to do things like livelihood distribution factors and such. So I already mentioned like item 5, how do you connect the beams? And again, we designed that connection essentially to accommodate the distribution steel that's specified in AASHTO. More questions on that we typically get. Number 9 covers top tension. That's an issue that we see in every pre-stress bridge to make sure we design them in accordance with the AASHTO LRFD. And as far as number 8 for connecting the beams, again, we allow reinforced concrete or UHPC. And more questions about confinement, which I'll cover the details in a few minutes. I'm just going through, just showing these FAQs are included. When it comes to the deck and wearing surface, there's a lot of questions about keyways and exposed aggregate, wearing surfaces, and can you build a bridge without an overlay? And the answers are detailed here. The answers are simply, we do recommend an exposed aggregate keyway. Wearing surfaces are optional. You can decide whether or not you want it, depending on which state you're working in. And recommended wearing surfaces, you could use asphalt. You could use a thin concrete if you desire as well. Railing questions. So how do you put railings on this? Well, use the same details you would use for an adjacent beam bridge you currently are using. Most state DOT bridge manuals include details for different railings and parapets with bars projecting out from the fascia beam. Let's see. We'll talk about variable height of the curb in a few minutes as far as accommodating roadway profiles. So now we get into the details. Enough of the text. So these are the actual detail sheets. The first sheet, sheet number 1, SDB1, covers a bunch of different topics. So we'll dive in. One is design and implementation guidelines. Understand these are guide details. These are not standards by any means. You still have to design the bridge as a designer, and we give some things that you are responsible for as far as design. You're also responsible for detailing the bridge as well. So all these items should be covered by the designer of the bridge. Now, as far as the beam cross section, I mentioned before, we are recommending 4 different widths of beams from 35.5 to 47.5 inches wide. Then we'll get to the depth in a few minutes, but basically we have variable depth and variable width. And you'll see later on, we'll talk about the closure joint between the boxes. You can vary that as well. So like the next beams, we can dial in an exact bridge width. If you desire a bridge a certain width wide, say 53 feet wide, we can produce a 53-foot wide exact bridge width by varying the width of the beams and varying the width of the closure joints. As far as beam depths, you look at note 3, we are recommending 4 beam depths, 12 inches, 15 inches, 18, and 21. Live distribution is always a big question with any new beam section. How do we calculate it? And as I said before, we are emulating a solid cast-in-place slab bridge. AASHTO has provisions for calculating live distribution using the strip method. And essentially, the diagrams on the right show strip width of E, which is the equivalent width of the lane on top of the bridge. So you go through the standard equations in AASHTO for strip width, which is a very simple equation, and you take that strip width, divide by the beam spacing, and you get a live distribution factor for the percentage of the strip that is supported by each beam. So we give provisions for interior beams and exterior beams. Very quickly, you can calculate distribution factors for these beams. If you happen to mix 2 different beam sections in a cross section, which occasionally happens, especially with stage construction, we give recommendations for how to calculate the distribution factor for the odd width beam or the other beams as well. Okay, the next sheet covers profile management. Like with next beams or any deck section, if you have a profile that's a tangent profile, which is shown on the top, or a crest vertical curve in the middle, or a sag vertical curve, there are several options for how to accommodate these curves, and they show up in the details shown on the screen here. The 2 options you have is you can vary the depth of the beam, as shown on the top, where you can actually fabricate a beam that varies in thickness from one end to the other. This does add cost to fabrication, so understand this comes at a cost, but you end up with a beam that essentially will match the profile of the road. Or the second option is keep the beam depth constant, and if you have an overlay on the bridge, you vary the thickness of the overlay to accommodate the vertical curve or the profile of the road. Understanding, though, this will affect the height of the barrier. So the engineer should be detailing, usually in a table, the height of the barrier from one end of the bridge to the other to provide the correct projection of the barrier above the roadway wearing surface that we require for these roadway barriers. So we're varying the thickness of the overlay, or option 1, we vary the thickness of this section. As far as reinforcing, an awful lot of time was put into how to reinforce these beams, and these details should be followed. I would not recommend making any significant changes to these as you detail the bridge. A lot of thought was put into how this works, and it affects the dimensions of the beam and the layout of the strands. So we're showing 2 layers of strands on the bottom. You notice in the corners, the lower corners, where we leave a strand out to accommodate the radius of the stirrup. We do have accommodations for top strand as well, if that helps your design. And again, showing the bars coming out of the side of the beam. And one of the key aspects of the bars coming out of the side of the beam is the location of those bars and the shear key dimensions go hand in hand. It has to do with the way they fabricate these beams. So essentially, the chamfer on the shear key is just inside the bars projecting on the outside to the outside of the beam. We'll cover that a little more later. As far as reinforcing, we have a whole bunch of reinforcing design and strand layout notes. I won't go through each one, but a few I'd like to cover. As far as the shear bars, the stirrups, we recommend keeping it to number 4 bars, and that maximizes the cover on the side of the box and the bottom of the box. So we recommend holding number 4s as your shear bars, which should work in just about every case. The second design note 2 is where we actually say that the hook bars that come out of the side of the beam have to meet the requirements for distribution steel specified in AASHTO Article 512.2.1. Again, in most cases, number 5 says 6 should work. The strand note number 1, you'll see straight strands only. Draped strands are not permitted. I mean, if you get in a bind and you really are trying to push a section, we can do draped strands, but you should probably contact PCI or talk to a local fabricator to see if they can accommodate draping. Not all fabricators in the region can do draped strands. They don't have the hold downs in their bed to handle draped strands. So by adding draped strands in the design, you're limiting how many fabricators can bid on a project, which could potentially lead to increased cost. So we recommend designing for straight strand with the bonding. Again, here's the detail showing the connection. And this is where what we have done at PCI Northeast is come up with simple equations to design and detail these joints. And if you see the joint on the upper left, that's a reinforced concrete closure joint. First, you have to calculate W1, which is the specified width of the joint. A very simple equation you can do in minutes. No, the first thing you have to enter in the equation is the lap length, L1. And L1, the ABC guide specification has requirements for that. Essentially, it's the development length of a hook bar. So we give recommendations for that. Once you know L1, you can calculate W1, the width of the joint that you specify. And then P1 is the projecting bar, the length that the bar has to project beyond the face of the unit. With those three dimensions, you can draw this detail and it can be fabricated. And the key thing is these details take into account tolerances as well. So if you follow these details and these dimensions, your beams should fit together and you will get the minimum lap splice specified, that L1 at the bottom. And you notice there's two small tables at the bottom of the details. We've actually gone through and done some preliminary designs for you. If you're using 4,000 PSI concrete for the closure joint and number 5 bars, we give you W1, P1, and L1. Likewise, if you're using UHPC with number 5 bars, we give W2, P2, and L2. You can, if you change the concrete strength, you can rework all these things. And keep in mind, these dimensions are the minimum width joints required. You can go wider than these joints. So say W1 is 13.5 inches. If you want to use a 15-inch wide joint, you definitely can. You just have to increase the P1 dimension, which is a very simple equation shown on the top of the detail. So this is notes about the closure joints. The key thing is I've highlighted a few of the items. The designers are responsible for verification of the design requirements for this reinforcing. Again, meeting the requirements for distribution steel, and they're following the provisions in the AASHTO LRFD guide specs for ABC, which has to do with the lap length of those bars. Keep in mind the width of the joints will affect the beam spacing. So if you go to a wider joint, your beam spacing increases, which will affect your lively distribution factors that we showed before. Item number 8, that the area of the bars in the closure joint are based on distribution steel for solid slab bridges, and we give the AASHTO article you need to follow. It's a very simple article. It's not a very complicated design. And then number 9, the committee set a maximum joint width of 18 inches for hook bars and 12 inches for UHPC. These numbers, understand, were essentially pulled out of thin air. It's just a gut feel. We wouldn't want to have a super wide joint between the beams. So you can't, if you have a bridge where you want to go 18.25 inches, that's fine. It's just something that we set a recommended maximum width joint for reinforced concrete and UHPC. Okay, this next sheet is, let me back up a little. This next sheet has typical section properties for beams and notes for bridge cross sections. The cross sections shown represent the typical use of spread beams with minimum width joints and maximum width beams. As you can vary the width of the joint, you can make it larger, and you can vary the width of the beam. You can make it smaller than shown here. In this case, they're 47.5-inch wide beams. So you have a lot of variability and adjustability. At the end of this presentation, I'll go through a spreadsheet we developed to help you develop a cross section for your bridge for, say, preliminary design or even for your final design. Note 3 says in special cases you can mix beams with different size beams to accommodate an exact bridge width. This typically shows up if you're doing stage construction and you have a stage construction joint that is in a certain spot that you can't move, that you may need to throw an odd beam in there. It does come at a cost, but you can definitely add 1 or 2 or several different width beams in a cross section to get the joints where you need them to be. We gave section properties for solid deck beams for different sizes. You can see we varied the depth from 12 to 21 inches, and we varied the width from 47.5 to 35.5. So it's all given to you right there. Nowadays, with computer programs, we can calculate section properties very easily with CAD programs, but we gave tables here for at least for preliminary design. People always ask about span lengths. What are the maximum span lengths? And what we're finding out here, we ran a whole bunch of different designs. And what we're finding, and the note on the bottom, really the bottom of the screen, tells the story, there are recommendations in AASHTO for minimum span depth ratios, and we can meet the span depth ratios in virtually every situation. In other words, if the AASHTO span depth ratio says you cannot exceed, you can't go less than 15 inches, we can meet that 15 inches every time. I think every single design here is I'm sorry, the span is greater than the minimum span depth ratios in AASHTO. But as you can see, we can span anywhere from 25 feet up to 55, 56 feet in some cases, depending on which beam you have. The span depth ratios are very favorable, very thin superstructures, and this will get you going for preliminary design. Now, understand there's a whole bunch of criteria that we use to establish these span lengths. We include them on the sheet. If you see here, these are the 15 assumptions that were made to develop those span tables. Any one of these assumptions may or may not be applicable to your design. So these are ballpark numbers to get you started with a preliminary design. Understand, I'm not guaranteeing these span lengths at all. And that's what the first note says on the top. Number two, these span lengths are based on beams with reinforced concrete closure joints. If you use UHPC, you can even go longer with the spans because the beam spacing gets tighter. We are neglecting the contribution of the closure joint and the strengths, which is another conservative approach. We're assuming the concrete and the closure joint is just dead weight and has no structural capacity. The reason for that is the computer programs used for designing bridges. You can design them for having a composite slab on top, but having a composite slab on the side is just not something these programs can't handle. So we take the conservative approach and just neglect the stiffness of that joint and just take it as dead load. Similar to the way we handle parapets on bridges, we don't accommodate the stiffness of parapets in our design. Debonding, we did not use any debonding for these span tables. You can get even slightly increase in span lengths with debonding. Moving on to details. Reinforcing details at skewed ends. Now, we do recommend a maximum skew of 45 degrees. And how this shows how you should lay out the bars in those ends to accommodate the skew. The key thing is the projecting bars into the closure joint should be kept perpendicular to the side of the beam to make fabrication easier and actually construction easier as well. Differential camber is something that we want to make sure we can cover, and we've concluded that a differential camber of about 1/2 inch is acceptable. The key thing with differential camber is you can get you start losing cover over the bars in the closure joint. So with a 1/2 inch differential camber, we can typically maintain 1 inch of cover in the bottom and 2 inches in the top. So this is why we set our differential camber at 1/2 inch between units. Okay, enough of the details. Now we'll walk into some photos. We always like to look at photos. This is photos from JP Carrera showing them fabricating these beams. Nothing quite too exciting here except for the fact that we have bars projecting from the side of the beam. Now you notice in the lower left photo, this is the trick and how it's done. The side panels that are used in these bridges are actually a 2-piece side panel, in the forms, I should say. The one piece shown is a plywood with vertical slots cut in the panel. So the vertical slots are used to push the bars through, and also when the side form is removed, so you can slide the form out perpendicular to the side of the beam. The question is, well, how do you keep the concrete from going out between the bars, top and bottom? You got these vertical slots. Well, the second piece that go in is the actual shear key shape that is slid into from the end of the form and attached to the side panel. So when you go to take this thing apart, basically, you detach the side panel from the shear key panel. The side panel pulls out perpendicular, and then you slide the chamfer form out the end of the beam. A little bit tricky, but the nice thing about our PCI committee is we have fabricators on the committee, and they have told us this can be done. It's all doable. So this is not a big issue with regard to fabrication. It's something they can manage very easily in the shop. Photo in the center bottom shows a completed structure. Completed beam, I should say. You can tell by looking at this beam, this is a beam, first interior, sidewalk bars. You can see the reinforcing coming up of the sidewalk, coming out of the top of the beam. So I mentioned before that you can have any bridge width. So how do we do that? And as I mentioned before, we can vary the width of the beam, we can vary the width of the closure joint, or we can do both. So the question is, well, how do you do that? Well, you can get out your calculator and figure this out. We've developed a spreadsheet that we are going to make available to everybody on the PCI Northeast website. A very simple spreadsheet that does two things. Where you could dial in the width of the bridge, and also it'll calculate liable distribution factors for you. Now, the spreadsheet is based on all the beams being the same width. If you have oddball width beams, throw it in there. Oddball is a terrible term. Differing beam widths, you may have to do some hand calculations, but this is not rocket science. We're just adding up the number of joints times the width of the joint, and the number of beams times the width of the beams, and adding them together to come up with a exact width of bridge. So we have a spreadsheet to do this. So what I'm going to do now is I'm going to pop out of here. And Sarah, tell me if you don't see this, but you should see now a spreadsheet on the screen.
Yep, we can see it.
Perfect. So this is a spreadsheet we developed. Again, this is not rocket science. This is very simple stuff. But say we have a bridge, and for an example, let's go through an example. Say I've got a bridge, and I've got a width of, say, 52.25 feet. That's the width of the bridge I'm trying to get. So that totals up to 627 inches. So now I have choices. Typically, we would recommend to start with the widest beam possible. Go with a 47.5-inch beam. And in this case, I've entered in 9 beams with 8 joints. And it tells me the width of the joint is 25 inches. Well, that's a pretty wide joint. And it says UHPC will work and reinforced concrete will work. But I don't want a 25-inch wide joint, so let's go to 10 beams. Change to 10. My joint's now at 16 7/8. They both still work. So if I was using reinforced concrete, maybe this might be the answer to my cross section. 10 beams, 16.7, 16 7/8 inch joint. Let's try 11. We go to 11. So now we're at 10.48. The reinforced concrete joint will not work in this case. It's too narrow. But the UHPC joint will work. We'll go back to say 10 beams. And that's 16 and a half. Well, let's try something different. Let's try going to a different width beam. Let's try one beam smaller, 43.5. Okay, now I can say I go to 11 beams, 14 7/8. Okay, not too bad. Or I say go to 12 beams. 12 beams, again, reinforced concrete doesn't work, but UHPC will work. So by playing around with these two numbers, the yellow are the input, and the output is the width of the joints. Pretty quickly you could hone in on a cross section that you want. What we do recommend is using a wider beam. The width of the beam, fewer beams that are wider are definitely less expensive than many beams that are narrower. So we typically recommend people start with the widest beam, and if the joint width isn't desirable, then start looking at other width beams until you get to a joint that is desirable. So say we've honed in on this cross section, we're okay. We're going to use UHPC joints at 9.5 inches. The output 9 4/8. This is a spreadsheet thing. So we're going to go with this design right now. And let's see, how do we calculate now a liable distribution factor? As I mentioned before, we're using the AASHTO provisions, Article 4623, and you can see the equation right here. The width of the live load lane is 10 plus 5 times the square root of LW. So we go in and say we have a span length of 45 feet for this bridge. You enter in number of design lanes. This is a 2-lane bridge. Our beam width is carried across from the first sheet at 43.5 inches. And then it calculates L1, W1, and W. Those are the L1, W1, and W are all defined in the AASHTO specs. And we go through and we come up with the E. For 1 lane loaded, E is 252 inches. For more than 1 lane loaded, E is 154 inches. You go through, so the answer is 154 controls. Our beam spacing is 53.05. 53.05 is the width of the beam plus the width of the joint. And it calculates the distribution factor of 0.345 lanes per beam. And there you go. You're off to the races. Now you got a distribution factor. You can now design the beam using any pre-stressed program that you have, where you would input the liable distribution factor versus having the program calculate it for you. And just to double check to see if that number makes sense. And in this case, it says there's 2.9 beams supporting each lane. So with a width of 154, the beams are 53 inches on center. Yeah, that makes sense. There are 2.9 beams underneath that lane width, the strip width, I should say. And so you divide one by the other, and you get 0.345 as your live load distribution factor. It really is that simple. We have some provisions for fascia beams, very similar equation for fascia beams as well, that you can do by hand. So go back to our PowerPoint. So that's how you calculate the width of bridges, and you can dial in an exact width, which is a huge improvement over the previously with adjacent box beams and adjacent slabs. We were kind of stuck with the width of the bridge, and we ended up varying things like shoulder widths to get it to work. But now we can actually, with a cross section given, with any barrier and any width bridge, we can dial in an exact width of the bridge with these solid deck beams. So, as we mentioned before, Sarah mentioned at the beginning, you're getting, if you want, you can get PDH credits for this presentation today. And if you're familiar with New York State requirements for PDHs, we have to have a quiz. So hopefully you are paying attention. So I have 5 questions that I'm going to go through now that you can answer on your own. We do not grade you on these. We ask you to self-grade yourself. Hopefully you all get perfect scores. So the first question, what is the term used to describe where precast elements are used in place of cast-in-place elements in a structure? A, replication, B, duplication, 3, C, emulation, or D, refutation? I'll give you a hint, it's not D. Give you a second to think about that. The answer is emulation. Emulation is a term that we use in the precast industry where we emulate cast-in-place concrete with precast concrete elements. The AASHTO, by the way, the AASHTO guide specification for ABC, virtually the entire basis of that guide specification is based on emulation. Question 2. How does an engineer calculate the amount of live load on a solid deck beam? We just went through it, so unless you're sleeping the last 5 minutes, you probably know this, but let's go through it. A, conservatively apply 1 lane per beam. Okay. B, use the PCI Northeast recommended approach that is based on the AASHTO provisions for slab bridges. C, use standard distribution factors for adjacent box beams. Or D, use a 3D model to determine live load effects. Give you a second to think about that. The answer is B, use the PCI Northeast recommended approach based on the AASHTO provisions for slab bridges. Question 3, 3 more to go. How can an engineer vary the overall width of the bridge with solid deck beams? A, vary the width of the beams. B, use different beam widths in a cross section. C, vary the width of the closure joints. Or D, all of the above. Again, we just went through this a minute ago, so this should be straightforward. The answer is D, all of the above. But understand that option B, where you use different beam widths in a cross section, does come at a cost. It can lead to higher fabrication costs because the odd width beam is going to have a different strand pattern, which means that beam will probably be cast on its own. So that could increase the cost dramatically because all the strand, a significant amount of strand will be thrown away in the bed because only 1 beam is being fabricated. So understand B is a last resort. Try to stick with A and C wherever possible. Question 4. How do you size the closure joint reinforcing in the connections shown? 1, just use number 5 bars. B, size the bars based on the AASHTO equations for distribution reinforcement in slab bridges. C, do a complete 3D analysis of the structure. Or D, call PCI and ask them. I'll give you a hint. Do not call PCI and ask them. It's not that complicated. C, 3D analysis, if you want to, have a ball. It's not required. The answer is simply B, size the bars based on the AASHTO equations for distribution reinforcement in slab bridges. And note that number 5 bars at 6 inches should work in almost every case. In reality, between you and me and the AASHTO code, if you come close, it's good enough. It's just distribution steel. So we try not to use number 6 bars. Number 5 should work every time. Number 6 bars, you'll have a little less cover in the beams, the top and bottom, but you could in theory go to number 6 bars if you have to. But 6 inch in the center, based on the forming, we recommend keeping a 6 inch in center cadence. And the last question. How do you design the lap splice and bar projection dimensions in the closure joint connection? This is down in the weeds here a little bit. A, use the equations and the guide details that account for tolerances. B, just use 12 inches wide for the joint width and 9-inch bar projection. C, complete a parametric study of beam tolerances to understand what you need to accommodate tolerances. Hint, that's what we did developing the detail. But then D, Call PCI and ask them. Well, we don't want you to call PCI and ask them. We're trying to make it easy for you. And the answer is quite simply A. We give equations in the guide details that account for tolerances, and they're based on the 2018 AASHTO LRF guide specs for ABC. The design of that joint can be done very quickly and very easily with essentially just calculating the development length of a hook bar, and from there you can design the joint very quickly. With that, that concludes our presentation. I wanted to leave plenty of time for questions and answers. We have a whole bunch of people here, 152 people online. So Sarah has been monitoring the chat box and the Q&A. So if you have that, Sarah, go ahead, fire away.
Yeah. So first, Mike's last two questions were trick questions because you can call me and ask me anything anytime.
I'm trying to limit the number of phone calls you get, Sarah.
That's all right. So first question was, what is UHPC?
That's a great question because we all take it for granted that people understand what UHPC is.
Yeah.
UHPC stands for Ultra High Performance Concrete. And I hate the term, to be honest with you. 20 years ago, we were talking high performance concrete. It was higher strength, higher durability concrete. And now we have ultra high performance concrete. What happens if we come up with something better? What adjective are we going to use to describe the next? Super duper ultra high performance concrete. But basically, what it is, it's a very high strength concrete combined with steel fibers. And steel's the key thing. UHPC, a significant amount of steel fibers are added to the mix to dramatically improve the tensile capacity of the concrete, which really affects dramatically things like lap splices and reinforcing development lengths. A good example, for a number 5 bar, typical lap splice with say 4,000 PSI concrete is somewhere in the order of 20 to 24 inches. With UHPC, a number 5 bar lap splice is 5 inches. So dramatically reduces lap splices, which makes it great for connecting pieces together. You can build beams out of UHPC. It's coming. It's not here yet, but it's coming in the industry. But for now, we're using UHPC to dramatically reduce the size of connections between precast elements. Another added benefit of UHPC, it's extremely durable. Even though it's loaded up with steel fibers, the permeability is so low that it's magnitudes better than normal concrete. So you get a really high strength connection, very short lap splices, and super durable connections as well. So it's what we like to refer to as a miracle material. It does come at a price. Its numbers have been thrown around in the order of $10,000 a yard, which I think is way. That $10,000 a yard accommodates not just the material, but also the labor to put it in and the forming to put it in. One added feature with UHPC that is you would not expect, it is very flowable. It flows like water, which makes the forming difficult because even a pinhole will leak. So you have to have really tight pinholes, but it's very easy to place because it's very fluid and it's super high strength and super durable. So it's a great material that we're using in the world of prefabrication, very commonly used. Some states use it quite a bit. New York State does quite a bit. Other states are using it. Connecticut uses it quite a bit. So the answer to the question is, if you want to use UHPC, check with your state DOT to make sure it's allowed. Some states do not allow it because of the cost. At $10,000 a yard, it's pricey. But understand, you're going to probably use 1 or 2 yards in the whole bridge to make these connections. So, even though the unit price is high, the volume is low. So it's not that big a deal. But a lot of states shy away from UHPC because of cost. So please check with your DOT before you specify a UHPC joint.
Excellent answer. Next question. Could lightweight concrete be used to further increase the potential span lengths?
The answer is yes and no. I'll qualify that. Yes, you could. We don't see a lot of lightweight concrete being used in the Northeast. There are some people have concerns over durability of lightweight concrete, and that's a whole other subject for another day. But other states are using lightweight concrete. The longest single span bridge in the country was built in Washington State. It's a 225-foot span pre-stressed girder, bulb T made with lightweight concrete. It can be done, but if you recall from the presentation, the span depth ratios that we could achieve with these solid deck beams is so long that deflection starts becoming the control. That we don't want to have too much deflection in the structure. So going much beyond the recommended maximum span depth ratios or minimum. I gotta do my math in my head, but you don't want to push it more than what AASHTO has, much more. You can go a little less. Again, if you want to go exceed the AASHTO recommended span depth ratios, you should inquire with the owner to make sure it's okay. But going to lightweight concrete, and I mentioned before, draping strands to push a span further out when you're already beyond the limits that are recommended by AASHTO. So the point is, you're not getting much bang for your buck to go to lightweight concrete, but it certainly could be done. Again, check with the owner before you do something like that.
Right. Next question. Have you looked into a shear key cross section with the bottom lips extended outwards? This would avoid the use of formwork underneath the joint. The detail is similar to the Florida slab beam bridge with UHPC closure port.
The answer is yes, we have. We've looked at that. We've looked at that detail a couple times, and it has to do with the way the reinforcing lays out. It can be done, but it does greatly complicate the forming. The thought was of the committee, the forming of the bottom of the closure joint is a relatively easy thing to form. Most contractors run a tie rod up through the joint to hold it in place, so it's a pretty easy form work to do. We like the Tappan Zee Bridge had a detail similar to what you're describing. It can be done, but the committee just felt it just complicates the forming, and there's also potential for that lip to be broken off during handling. So we're you could try to detail something like that, but really talk to fabricators before you try doing something like that because of the issues and the complications with forming.
All right. Is there guidance on how we can calculate or confirm the number 5 bars at 6-inch spacing are adequate?
Yeah, I actually have a spreadsheet I've developed. I guess I could bring it up. Let me see if I have it handy here while we're talking. Um, I don't have it handy. I'm sorry, but it's a very simple equation. Essentially, what it comes down to, like any distribution, get this out to me. Any distribution steel in a slab of either a deck slab or a slab beam, it's a percentage of the main steel. So you can end up around 50% of the main reinforcing. So if you, whatever you have for bars running lengthwise, and the AASHTO equations do accommodate pre-stressing strand versus rebar. So it's a very simple equation. You run a few calculations on the stress in the rebar, or the stress in the strand, or the area of rebar, and the answer comes out as a percentage of the main reinforcing. So it's a very simple equation. I don't have it handy with me, but if you can look up the AASHTO provisions for slab bridges for distribution steel. I gave the article number in the presentation. It's very simple. It's a 5-minute hand calculation once your beam is designed.
Any more questions? We'll give it one more minute for people.
If you give it, if there's more questions, I will look for that spreadsheet. I can show if we get some time. I might as well do it. So I got to go to. Wait 2 seconds. Go get
As
it
Mike
going.
said, the other Excel sheet that he just shared, we are going to share that on our technical resources page on the PCINE.org website. That will be posted later this year after our bridge committee does a final check on it.
Okay, I found my spreadsheet. So this is, you should be able to see this. This is the calculation for distribution of steel according to AASHTO Article 5922. And it basically, the first bullet is for reinforced concrete. We're in the second bullet, which is longitudinally pre-stressed concrete. Essentially, you run through the simple equation. FPE is the effective stress in the pre-stressing steel after losses. You can get that from your design program. L is the span length, and you can see it maxes out at 50% of the steel. So this table up here, I took 2 bridges that were built in Vermont, the photos that we saw before, and went through the calculation, and I came up in, you could see, perhaps we may make this spreadsheet available to Sarah, to people to try. It's a pretty straightforward thing to do, but basically in this case here, the first one, number 4 is at 6 worked, and the second one, number 5 is at 6 worked, and this is for a span of 36 feet for the Woodstock Bridge, so you can see the calculation. It's a very straightforward calculation. We could make this available, but it's simple. And like I said, we ran through a bunch of different beams and basically 5s to 6. In this case, 5s to 6. The required steel is 0.449. We're giving 0.610, not even close. So 5s to 6 should work just about every time.
All right, one more question came through. Can we use 5,000 HP concrete for the beams?
For the beam, the answer is talk to your state DOT, and there's no reason why you couldn't. Most states have in their bridge manuals have certain concretes they allow or they recommend for design of pre-stressed beams. Talk to the owner. I wouldn't do that. I wouldn't violate a DOT bridge manual unless you really get permission to do so. There's probably, there's no reason you couldn't use 5,000. But in the world of pre-stressed concrete bridges, we rarely go below 6,000 for our 28-day compressive strength. You could do it, but we typically see 6 to 8,000, sometimes even 10,000 in our region.
Yes. Another question came through. Thank you for a wonderful presentation. Will the spreadsheet shown for typical cross sections be on the PCINE website? Yes, we will have it up there. It's not going to be in the next 2 weeks, but it will be later this fall.
Yeah. Yeah, we want to make sure it's correct, and we're having members of our committee are double checking the math. I'm pretty sure it's correct, but we want to make sure before we publish something that it's right there. And perhaps even this spreadsheet, we can do a similar thing with this spreadsheet where you can use it for calculating distribution steel based on the ASHA equation. As you can see, the ASHA equation is, again, not rocket science. We're talking an equation where you have to get one number from your output. In this example I gave, I just assumed what FPE was for the sake of this calculation. I'm assuming 185 KSI, but these are output you get on your computer programs. And once you get the computer program output, I'll walk through it really quickly. You go in with span length. You have to. I did assumed FPE, but you'd actually get the actual FPE from your output. Total number of strands in this case here, I'll just use the Woodstock bridge. There were 234 strands in all the beams for the cross section. Total bridge width was 56.33 feet. So I calculate the number of strands per foot of bridge width. So we have 4.15 strands per foot. The area of those strands are 0.216 inches. So we have a total area pre-stress per foot of bridge width. We're doing everything by per foot is 0.893. Percentage of the main steel. You go through the equation down below, you get 51%. The maximum is 50. So you take 50% of this 0.8973 and I get 0.449. It's that simple a calculation. You try to break everything down into area of steel per foot of bridge, and you give a percentage of that area of steel per foot of bridge in the transverse direction. It's that simple.
Excellent. Well, that's all we have for questions, and we are running up against it for time. So,
Perfect.
Mike, I'll mirror all the comments that are filling up the chat. Thank you so much for this presentation. You make it really easy to understand. So we're
Thank
all
you.
excited that you just did that, and PCI is thankful to Mike and the entire bridge committee who continues to solve problems when it comes to bridge beams and how to do things better. So thank you, Mike. Thank you, everybody, for taking an hour out of your day to join us. And be on the lookout for these spreadsheets posted later this year on the PCINE Technical Resources tab.
Yeah. In the meantime, the details are available today.
Yes, they are.
Excellent.
All right. Thank
Thank
you.
you.